Okay everyone, let's get started. Today my plan is to finish my lecture on MIPS Microarchitecture and hopefully give you enough so you can finish the lab. So last time I introduced or I reviewed MIPS ISA. We've got the R-type, the I-type, and the J-type instructions. It's important that you know how those work because that is going to define how you design your CPU. I mentioned we've got 30. Our goal is to implement 32 instructions or to support 32 instructions. The ones in red are the ones that we'll be implementing in this lab, and then in the next lab we'll add the ones that are in black. That also implies that we're going to be dropping one of the labs. We got a little bit behind because we extended the RPN calculator, and I also missed a lecture because I think I spent a lecture reviewing for the exam. So I think we're behind by 1 or 2 classes. So instead of doing the CPU in 3 phases like we originally planned, we're going to just do it in 2. So there's going to be a little bit more work in the beginning since we'll have more instructions in the initial version of the CPU. Basically, we're going to do all of the number crunching instructions, and we're not going to do load, stores, or branches until the next lab. So these are the ALU style instructions, essentially. And it looks like there's a lot, but there's a lot of overlap between them. I mentioned last time, I think that, add and subtract are pretty much the same instruction, except the ALU code, opcode, is different during the execute phase. So it's not as much work as it might seem. So we have Mars installed in the lab machines, and I'll be reviewing that today as well. You can start that up in Linux by typing java --jar and then the path to Mars, which is in user local third party. Do you all remember Mars? You all used Mars, right? Yeah. Okay. Okay, so we have some options on how to design the CPU, but at some point a few years ago we decided to put the instructions in the data memory on chip as opposed to having to deal with an off-chip memory, which requires that you have a controller, like a DRAM controller, that you have to interface with. One of the implications of that decision is that the memory that's on an FPGA, and in the case of the Altera FPGAs that we're using in class, they're called M20Ks. Actually, I think they're M4Ks, right? Or M9? What do we have on these one?
DE2115 is M9.
M9K, yeah, sorry. So there's these M9Ks, which are arranged usually in 4 or 5 columns on the FPGA grid. And they, as the name implies, they have 9 kilobits, right? 9 kilobits of memory in each one. The thing about them is, though, that they have limitations on how you can use them. One of the limitations is they have 2 ports. You can't access them with more than 2 ports. And the other is that they have synchronous reads, which means that when you read from them, you don't get the data that you're reading until the next clock cycle, which I'm trying to show, which is what I'm showing here in this timing diagram. So I have A1 is the address that's going to give you the contents of address A1, which is D1. And you'll notice that D1 comes up in the next cycle. So there's almost like basically a delay between when you ask the memory to read and when you actually read. Make sense? So this is going to affect our instruction memory and our data memory. So when we fetch an instruction, we're going to have an address for that instruction that's stored in the program counter, but we don't get that instruction at the address in the program counter until the next cycle. Likewise, if we do a load instruction, we have to load data from memory and we get it in the next cycle. So that gives us a lower bound on how many cycles it's going to take to execute an instruction, you have to design your CPU for the worst case. So if you do a load instruction, it takes 1 cycle to get the instruction, 1 cycle to execute it and calculate the address, and then access data memory. And then when you access data memory, you actually get the data out of memory the next cycle, so that would be the 3rd cycle where you write it back. So we're designing a 3-stage pipeline, which is similar to the 5-stage pipeline that you should have learned in 212, except it's simplified. You don't have to worry about, it's a little less complex to design. Okay? So I tried to show that here. So if you have an instruction that's depicted as the color gray, then it would be fetched in 1 cycle. We'd go through the decode, execute, and memory in the 2nd cycle, and then the write back would happen in the 3rd cycle, right? And the memory latency, and when I say memory latency, I mean the time it takes to access memory, would be 1 cycle from cycle 1 to 2 for the fetch, and 0 to 1 for the fetch, rather, and then cycle 1 to 2 for the memory operation if you're doing a load. You guys with me? Latency being, how long it takes to do memory operation. Okay, and then because it's pipelined, we can, you say, well, that sucks. We got to wait 3 cycles per instruction. That's a long time. But if you pipeline it, you can execute 3 instructions at one time. And that way, it still takes 3 cycles to finish 1 instruction, but you finish 1 instruction every cycle, so it's like a car assembly line, right? Now I found that this makes the Verilog design confusing because you have all these signals in your design, and sometimes it's hard to tell what signal, what's going, or what, for like if you're simulating your processor and you look at a moment in time, what signal is corresponding to what instruction, right? That's the tricky part. You guys with me? Like for example, you got muxes, right? You got mux inputs and mux outputs, and you have values going to ALU, and you see them all in the simulation, but you need to make sure that you understand which phase of the instruction execution is corresponding to each signal. So my solution to that is to add a suffix to the end of all your signal names. So you can say _fetch for signals that are in the fetch stage, _ex are signals that are in the execute stage. And when I say execute, I really mean the middle stage, which is decode, execute, and memory. And then _write back is for signals that are in write back. So if you stop the simulation and you look in 1 cycle, you can associate 3 different instructions depending on which signal you're looking at. You guys with me? Now the thing is, the practical matter is that there's not a whole lot of signals in fetch. It's basically just the program counter. And there's not a whole lot of signals in write back either. It's really just the signals that are involved with the write port on the register file. So most of the signals are in execute that you see, right? Okay. So the fetch stage, as I mentioned, is really just for now is just until once we put branches and jumps in, this will get a little bit more complicated. But for now, because we don't have any branches and jumps, the fetch stage is just the program counter with an add by 1 circuit on it that adds 1 every cycle. And then there's also an instruction memory that's part of that stage, and then it spits out the instruction. You guys with me? So when you think about this, that's a register. I should have colored that. This should be gray to stay consistent with my coloring scheme. I just noticed that now. So this is a register, program counter. And so if I were to stop this and look at these signals, I might have 10 right here, address 10, right? And then there's an instruction coming out, but that's going to be the instruction that's at location 9, because in the last cycle I was putting 9 in, So in the current cycle, I'm getting the contents of address 9, but the value going in is 10. You guys with me? So whatever's coming into this is going to be lagging by 1 cycle. I'm putting 10 in, I'm getting the address of 9 out, and then this guy is going to be 11, right? Because I'm going to have an 11 on this wire coming in, I'll have a 10 coming out of here, and I'm going to have the contents of address 9 coming out of here. So there's kind of, you can kind of see 3 cycles worth of activity here. You guys with me? Right, because it takes a cycle to get a new PC, and it takes a cycle to get the instruction out of the memory. Okay, and then I mentioned that you can use Mars to initialize the instruction memory, and I don't know if I updated Dropbox yet, but this is actually the code. I gave you the code for the instruction memory here. So there's an initial block that loads the hex code in. The hex code is what's produced by Mars, which is the assembled version of your assembly language code. So you write assembly language, you export it as a hex code, and it will get pulled into your instruction memory Verilog. A few years ago, one of my grad students figured out that there's a way that you can initialize the instruction memory after you program the FPGA. In other words, you could put the CPU on the FPGA and load a program in, right? But we found that we never needed that because it doesn't take that long to recompile, your design. And so basically, when you do it like this, you have to recompile your design every time you want to change your program, which might seem inconvenient, but there is, just rest assured, if you wanted a way to reload the program after you compiled and programmed the FPGA, it's possible to do that through a tool called the In-System Memory Content Editor. But as it stands, the way this is set up, if you want to tweak your program, you have to recompile, which means that you probably want to make sure your program works in Mars before you do this, because debugging your MIPS code through your own CPU is problematic, not only because you have to recompile your whole Verilog every time and reprogram the FPGA, but when you have a problem, you don't necessarily know if it's a hardware or software error. Of course, you could simulate this in ModelSim too without recompiling it for hardware. That would be an option as well. But in general, it's best to sort of make your MIPS code somewhat bulletproof before you put it on the hardware, because you don't want to get into a situation where something doesn't work and you don't know if it's a hardware problem or a software problem. Okay, so let's see. EX stage starts out pretty simple for just the R-type instructions, because the instruction, after it gets spit out of the fetch stage, you can grab the R, S, and RT fields, right, and just plug those into your register file. And then you can take the instruction, all the control bits of the instruction, which is the function code and the shift amount, 10 down to 6, and you can put those in your control unit. And then, now you might say, well, wait a second, why don't you just take the RD field and plug that into the register file? Well, you can, except you have to be careful there, because the RD field in the instruction is something that's not used until the instruction gets to the write back stage. So you have to put a little delay in here. You guys with me? So register, you delay that by 1 cycle, right? So you defer the writing of the register until the next cycle. Now, I probably should have showed the register file is part of the write back stage, so I could have just, I guess I could have just drawn this arrow back up in the register file, but I wanted to show that this signal was something that was being, pushed into the write back stage. Does that make sense? Okay. Okay, so likewise, we want to delay the reg write signal and the reg select signal. And then you want to have the output of the ALU, likewise, you want to delay, you want to register all those because you want to push those into the next cycle. So basically what this comes down to is any signal you want to send into the next stage, you just put into a register, a delay register. You guys with me? Okay, and then that reg select is selecting the data that gets written back. So the reg dest is the RD field, delayed RD field. But the data that you write back to the register file needs a mux that selects between the registered version of the undelayed, delayed low from the ALU, and then high and low registers. Does that make sense? And the reason for that is because there's 3 possible things that you would be putting into the register file. R, high, or low, at least for now, right? Okay. Okay, and then for the I type, which we're also including the I type instructions, there's a few additional modifications you have to make. You have to extend the B input on the ALU with a mux that allows you to select between an R-type instruction, which is 2 registers, versus an I-type, which has the immediate value coming in. Make sense? Because with an R-type, you always send the contents of 2 registers in the ALU, and with an I-type, it's 1 register in the immediate. So this mux here is giving you an option. Likewise, and this is something I think is a dumb decision on the part of the MIPS designers, but they had this thing where the destination register is RD for R-type and RT for I-type, which there was no reason they had to do that. I mean, they could have just made it RT for both, and then you wouldn't need this mux. But they have this, the destination field is different in the 2 instructions, so you need a mux for that. That was fixed in RISC-V, like I mentioned. That's one of the things they changed in RISC-V. Okay, and then, okay, this is the data memory, and we're not doing data memory instructions. We're not doing loads and stores, so that slide should actually not be here. In fact, I'm going to delete that right now, and I'll update that. Okay, and then this slide just shows that we have this GPIO In is an additional option, which is for, I mentioned last time, we want to have a special way to get data in to the CPU. So there's a little hack that we have for that. But the point here is that once you have these muxes, it's not too hard to extend them. Like if you want to add functionality, you want to add instructions, a lot of times it just involves taking these muxes and adding ports, and that gives you additional data paths that you can use when you're executing an instruction. Hopefully when you guys took 212, you had a test question about that where it would say, what would you have to do to add this instruction? I used to always ask questions like that. Sometimes I would have instructions that don't even exist. I would say like, what would you have to do to add a load and increment instruction that would, or store an increment rather, where you would store a value, but then it would also update the base register with the original base register plus whatever the offset was, right? Kind of like an auto incrementing thing. And so a lot of times that just involves adding paths, adding data paths, or sometimes just adding control signals. Okay, and then I think I mentioned this last time, but we need a way to get data in and out. Normally you do this through load and store instructions, but we don't have load and store instructions yet. So we added this little hacky thing where if you do a shift right arithmetic with a 0 offset, it'll bring in a GPIO signal. And if you do a shift right logical with a 0 offset, it'll write a GPIO out. So this is what I believe to be the full, this is the block diagram for everything in this lab, I think, right? Am I forgetting something here?
The bottom right mux, the inputs are mislabeled. R right back should be high right back.
Oh, yeah, you're right. Thank you. Yeah, I didn't notice. Okay, well okay, good catch. So this one should be actually right here. This is low, right? Yeah, and this one is not R, but high. Yeah, they were scrambled. And this is R. All right. By the way, R stands for result, but it really is just the delayed form of low, right? But we couldn't call it low because we have another low, which is for saving the low from a multiply. You guys with me? So if you can take this and translate it to Verilog, that's essentially what the lab is. That's what we want you to do. And you have the ALU, the register file. So really it's just about, you have to create the instruction memory, which I actually gave you in this slide deck, and the control unit, which is just a big if-then-else statement. I gave you some examples of that. So really it's just about kind of just converting this into Verilog, this block diagram. But I'm gonna get you started though. But before I get to that, we want this CPU to do something useful. So I came up with this idea a few years ago, which was you put a value on the switches and it'll convert that from binary to base 10 and display the output on the hex displays. You guys follow that? So like if you take the rightmost 4 switches and move all of them up, that becomes 1 1 1 1, which is F, right? Now, if you were just doing binary and putting that out to the hex displays, it would say F, right? But if you convert it to base 10, you would say 15 1 5, right? You guys with me? So we want to be able to write a program in MIPS that not only reads the value from the switches, but does has software that does a base 10 conversion, and then outputs that to the hex displays. Now, someone asked me a while ago, like, why not? I mean, we've got the hex displays themselves are all just custom hardware, right? You got hex decoders. So why not? If that's what you want to do, why not just make a custom hardware design that does a base 10 conversion? I think someone actually found one online that'll do it. But that's possible, but that's not the point. We want to make a CPU, right? We want to make the CPU, which we could write programs for the CPU much more easily than we could do custom hardware, right? Okay, so how do we do the base 10 conversion? Well, the easiest way to do it is just to take the number and do a modulo 10 operation, and that'll give you, if you do a modulo 10, that'll give you the rightmost digit, right? So like if you have 5,678, modulo 10 is 8, right? And then you can delete the least significant digit by dividing by 10. And then then you do the modulo by 10 again, and then divide by 10. If you do that 8 times, it'll translate 8 digits. Yes?
So we're basically unrolling the loop?
Yes, yeah. So we don't have...
You have while, val,
Right, so this is the pseudocode. We can't do a while because we don't do branches, so you can just unroll it, yeah.
Okay, and because the program counter will just loop around.
Right. Yeah, so the program counter, once it drops off the end, it'll go back and it'll basically become an infinite loop. Which is good because that way it'll continuously convert.
Displays.
Yeah. Okay, so how do we do modulo and base, and how do we do divide? It's actually not that hard. We have to use fixed point arithmetic. So I think I covered fixed point in here, right? Or am I thinking? Okay, yeah.
It'd be good to work an example. Maybe.
Sure, yeah. So fixed point is where you use an integer and you apply a scalar to the integer. So if you have, let's say you have an 8-bit number. So there's 8 bits, and you just treat it in your code as if the decimal point is here, for instance. So like you're going to treat all those 8 bits as being fractional bits to the right of the decimal point. That makes sense? I should be calling it a radix point because decimal implies that it's base 10, but I'm talking about binary number, right? So that means that this bit, that's the leftmost bit, the most significant bit, would carry a significance of 2 to the minus 1 power, right? And then this guy would be 2 to the negative 2 power, 2 to the minus 3 power, and so on, right? And then, so like if I have a 1 in this position, then that would contribute 1/2. If I add a 1 in this position, it's 1/4, this is 1/8, this is 1/16, this is 1/32, and so on, right? So if I had a number like this, if I had 0, 0, 1, 1, 1, then that would be 1/8 plus 1/16 plus 1/32 would be the value being stored in there. But another way to think of this, which is even easier, is like let's say those are all your bits, then you just say, well, that's 7, right? 7 over whatever the value is in the least significant position, which in this case is 2 to the minus 5th, right? Right? So that's actually 7 over 2 to the minus 5th, right? Or actually 7 times 2 to the minus 5th, or 7 over 2 to the 5th, I should say. So that's 7 30-seconds, right? Right? That way I don't have to add up. I don't have to add all these, these powers of 2 up corresponding to each of the 1 bits. If I just take the value and just multiply it by whatever the unit in the last place is. Yes?
Where does 7 come from?
The what? 7? Oh, the 7 is this 111.
Oh, okay.
Yeah. Yeah, it's the value.
So like in the slides there, because there's 4 places after the decimal point, that's where the 16 is coming from?
Yes,
The little
yeah.
13.
That's right.
16?
That's right, yeah. So this is 13. It's 13 is to the right of the decimal point,
Right.
and there's 4 bits to the right of the decimal point, and 2 to the negative 4th power is 16. So this is 13/16, right? That's just another way to think of it, right? But in reality, you're actually adding up 1/2 plus 1/4 plus 1/16, and that's the same as 13/16. And then any bits to the right, any bits to the left of the decimal point just get added as integers, right?
As they normally would.
So this would be 2 plus 13/16. Now you might say, well, what's the point of all this? Who cares? Well, this allows you to do fractional math without floating point, right? The only thing you have to do as a programmer is keep track of where the decimal point is. So you want to make sure that if you have 2 integers that are fixed point, if you want to add or subtract them, then they better have the same decimal point location, the same scaling factor. And that's all something that's just enforced by your code, not by the hardware, right? Likewise, if you multiply 2 fixed point numbers, then you have to add decimal points. So if I had 2 numbers like this and I multiplied them, I would no longer have 4 fractional bits in the product, but I'd have 8, right? You guys with me? Okay. It works the same way in decimal too, right? Like if I have 1.5 times 1.5, it's like 2.25, right? Whatever. It's the number of fractional digits in the product is the sum of the fractional digits in the multiplier multiplicand. Okay? So how does this apply to this lab then? Well, instead of dividing and doing a modulo, you can divide by multiplying by 0.1. So you can convert 0.1 to fixed point. You might say, well, how do you do that? It depends on the number of fractional bits. But in general, if you have n fractional bits, then 0.1 would just be would be 0.1 times 2 to the nth power. You guys with me? I mean, let's go back and apply it to this, right? If we have 4 fractional bits, then how would I put 0.1 in here in decimal 0.1? 1/10. How would I do 1/10? Well, it would just be, 16 divided by 10, right? Right? Which is 16 divided by 10, be 1.6, and I have to round it. So when I round it to get as close as I can, 1/10 would be 0.0010, would be 2/16, or 1/8, which is the closest I can get with only 4 fractional bits. So there's going to be a round off error, right?
Is there a particular direction we want to round? Is it like floor or ceiling? Or
I always do rounding to whatever the nearest is, right?
Closest?
Yeah.
Okay.
Yeah, so, and I actually ran into an issue with this earlier today when I was refreshing my memory on this. So what I suggest, well, hold on, I'll get back to that in a minute. So wait, let me get back to the algorithm. So the algorithm is then, you take the number, and instead of dividing by 10, you multiply by 0.1. And then you take the fractional part. Now, obviously, multiplying by 0.1 divides the number by 10. But if you can access the fractional part and then multiply that by 10, you can recover the modulo. So what I mean by that is, if you have 54, you multiply that by 0.1, that's going to give you 5.4, right? Then you can round that down and recover the 5. And if you take the fractional part, which is the 0.4, and you multiply that by 10, 0.4 times 10 is 4. So that's your modulo. That make sense?
You're taking your modulo 1. Right?
I'm sorry?
You're taking your modulo 1.
That gives you modulo 10, right? So you take, yeah, you do 54 multiplied by 0.1, that gives you 5.4. You separate out the non-fractional and fractional parts of that. The non-fractional is just to divide by 10, right? Is the quotient after having divided by 10. The 0.4 is going to be the fractional part, and if you multiply the 0.4 by 10, that will get you back to 4, right? So this is where the high and low registers are going to come into play, because if you take the number that the user enters and you treat that as an integer with 0 fractional bits, which, yeah, if you take the number that the user puts in that's an integer, and then you multiply it by 0.1, where the 0.1 is a 32-bit number where all the bits are fractional. Right? So what does that mean? What is that number actually? Well, it's 2 to the 32nd power, which is 4.2 billion, divided by 10 is 429 million and change. Okay, so you'll end up with the number the user entered, and then you have 0.1 as 32 fractional bits, and then you multiply them. And what happens if you have 0 fractional bits and you multiply it with a number with 32 fractional bits? Well, the product will have 32 fractional bits, which means that it will be split between high and low. High is will give you the non-fractional part, and low will be the fractional part. You guys with me on that? Right? Because you're multiplying two 32-bit numbers, you get a 64-bit result, and because one of the numbers originally that you multiplied had 0 fractional bits and the other one had 32 fractional bits, the product will then have 32 fractional bits in the low register, and all the non-fractional bits will be in the high register. So it'll be split there for you, very easy, nice and straightforward, right? And then you can use move from high and move from low to recover those pieces of the data. right? So this is where you have to round, by the way. When you take 2 to the 32nd power and divide it by 10, you get a fractional number. You have to round it up to this, 429,496,730. Because if you don't do that, you'll end up with some round off error in certain cases.
That's so cool.
Make sense? Yeah, actually, I'll show you an example of that here in a minute in Mars. Everyone okay with that? Okay. So that's basically for every digit, you multiply twice. You multiply once by 0.1, you multiply again by 10. Okay, so that's all I've got for the lecture. So now I want to go back here and talk a little bit about like how do we get started with this. And this is kind of the hardest part. Like this is the diagram. So you have the hardware and you have an algorithm for the software. So where do you begin? Because we don't give you that many guidelines on how to get started. In fact, this design is kind of is flattened. I didn't decompose this into modules because it's hard to show that on a slide. I mentioned last lecture you can put these in modules and you can organize this however you want, or you can put everything into one file. It's up to you. The way it's shown is it's just shown as flattened well, not really flattened because each of these blue boxes is a module or could be a module. Right. But how do we get started? One way to get started is to start with a program, right? And then start building the hardware to store and fetch the program. So let's open up. I don't have Mars. Okay. Well, let me show you how to get Mars. So if you go to Mars MIPS Simulator. And download it. And it's on the lab machines already, but I'm just going to go ahead and grab it if I can. Download. Okay. Stick it on my desktop. Okay. And Mars is great because once you've got it, oh, no, I can't run it. Okay. All right, well, I'll have to run it in Unix then. I should have tried that earlier. I guess I don't have Java on here. Okay, no problem. I'll run it in Linux then. Okay, so java-jar user local third-party CAD setup files Mars. Oh, sorry, not CAD setup files. Mars, all caps. Nope. Sorry, 611. CSCE 611, then Mars. Yeah, there we go. And Mars.jar. All right, there it is. And let's do new. Create a new assembly file. I'll start out with .text to tell it it's the text section. And then let's just build out one of the digits for our loop, for our conversion loop. So the first thing I got to do is I need to get the values of 0.1 and 10 into registers. Right? So I'll use a load immediate instruction for that LI. Actually, I'm going to tab that over like that. And so I'm going to use register 2 for 0.1. And so 0.1 is 2 raised to the 32nd power, which is that, divided by 10, which is that. So I'm going to take this and then I'm going to round it up. Whoops, 30, there we go. Take the commas out, 429,496,730. So I'll put a comment here that says regs of 2 is going to get 0.1, and then I'm going to load register 3 up with 10. Let's say regs of 3 is going to get 10. And then, now the next thing I got to do is I got to get the value that the user has on the switches. So normally the way you would do that is through a shift right arithmetic instruction. And if I had listened to Charles, we would have implemented that here. But for now, I'm just going to do a load immediate, and then we'll swap in the shift right logical before we put this on the board. Or actually, before we test it in model sim, I should say. So for now, I'm going to say load immediate, put that into 4, and I'm going to put the value 2, 3, 4, 5, 6, 7, 8, 9. So that's an 8-digit number, which I'm going to assume that I'm coming in from the user. Now actually this value is impossible. The board only has 18 switches, and I think the 2 to the 18th power minus 1 is the largest switch value I could put in, right, which is 256K. 256,000 something, or actually it's 230,000 or whatever. 256 times 2 to the 10th power, right? So I can actually only get a 6-digit number in on the switches on the board. You guys follow that? Because there's 18 switches. I can only get 6 decimal digits. But for this test, I'm just going to go buck wild. I'm going to put a full 8-digit number in here, right? That's an 8-digit. That's a huge number. Okay. So I'm going to say user input replace with SRA. Okay. All right, so now I need to extract the rightmost digit, so I'm going to try to get that 9 out of there. So I'll multiply I'm going to multiply register 4 with 0.1, which is in register 2, and then I'm going to do move from high. I'll put that in register 5. So regs 5 is going to be my whole part of product. And move from low 6 will be my fractional part of product. And actually, I think I'm going to change this up a bit, though. I'm actually just going to say, I'm just going to put this in 4 instead of 5, because 4 is where I'm going to keep the number that the user put in. But I might as well just, when I multiply by 0.1, I might as well just take the whole part of that and just put it back into 4. That way, I just maintain register 4 as originally it's the number the user put in, but I'm going to keep, reducing it by 1 digit at a time. You guys with me? So I'm going to recycle register 4 there, and then 5 I'm going to use for the fractional part. All right, everyone see that? I don't know if you can read that. Let's see, can I make that bigger somehow? Oh yeah, there we go. Oh yeah, there we go. Okay, that's better. Okay, now what? Well, I gotta do something about the fractional part. So I'm going to say I'm going to multiply the fractional part, which is register 5. I'm going to multiply that by register 3, which is where I put my 10. And now register 5 has the, or actually not register 5. I have to do a move from high. And I'll just recycle 5. So register regs 5 is now holding the modulo value. So I recycled register 5. Originally it had the fractional part, but once I multiply that fractional part by 10, I don't need it anymore, so I'll just reuse that. Okay, so now is the tricky part, because I've got the modulo value, right? But the next time I do this, I'm going to get another modulo value that's going to have to be put to its left. in the final result, right? Because I'm assuming that our result will be a 32-bit number that's divided up in groups of 4 bits that will be a decimal values, a BCD, binary coded decimal. You guys with me? So I want to be able to concatenate all those digits in one value. Yes?
So like 4 bits per digit, basically?
Yeah. Yeah, so there's a number of ways you can do that. I think one way to do it is to take that value and shift it to the left by 28 bits. You might say, why 28 bits? Because every time I extract the digit, I'll put it on the left-hand side of the register, and then I'll shift it down by 4 bits each time. And after I do this 8 times, that first value will have worked its way down to the least significant spot. So that way,
Wait, does it start with the least significant digit or the most significant?
well, once I've done the, once I take the fractional bit, multiply it by 10, it'll be in that number should be in the rightmost 4 bits, right?
Okay.
Because it'll be right justified, right? But then I want to put it on the left because I want to treat the whole thing like a giant shift register. I want to work it way down, so I'm going to shift that to the left. Likewise, I'm going to shift the other, whatever value that I'm storing the final result in, to the right by 4 bits. So I'll use register 6 for that. And then I'm just going to OR those two guys together. So register 6, and register 5. And actually I need, this should say 5 here as well. Yeah. All right, so I'm going to take, so I'm going to have this register 6, which will be my final number, my converted value. So this will be in, this will have spot for 8 digits. So there's 8 digits in there. And every time I convert a digit, I'm going to send it into the leftmost spot. Well, actually, I'm going to shift the whole thing down and then send the next digit in the rightmost spot. Sorry, the leftmost spot, sorry, right? So I'm going to start out with, like, say, 2 in there, right? And then when I convert the next digit, I'm going to shift that 2 down to this position. I'm going to put the next digit there. And when I do the next digit, I'll shift it down again and just keep adding digits to the left, right? And right? You guys with me? Why is that? Well, because every time I do this modulo thing, I'm getting the rightmost digit from the number I want to convert, right? And so I'm working my way from the right to the left, right? So when I put the numbers into the final result, I want them also to go from right to left, right? But I'm going to put them in on the left-hand side and shift down. It's just a trick. There's other ways to do it too. So the reason I'm doing it this way, by the way, is because then I could take this code and copy and paste this 8 times and I'm done.
Yeah.
Right? So this is one iteration of the loop. So
Well, you would copy paste it, but just alter the shift amount?
no, you don't have to alter. That's the beauty part. See, I don't have to alter the shift amount because I'm always taking the newest digit and inserting it on the left-hand side of the value and then shifting that value down to the right. So eventually, after I do this 8 times, the first digit I converted will have shifted all the way down to the right-hand side.
Oh, okay. I did it a little differently, where I just shifted everything to the final position and ordered it.
You could do it that way, but then you can't. Then every iteration is different.
Each one individually.
Yeah. Now, if we had shift variable instructions, which MIPS does have, it would be easier that way, I think, because then you could just have a counter. We don't have shift variable instructions, so without those, I think this is the easiest way to do it. All right, so then once I'm done, I have to send the result out to my GPIO so the user sees it on the displays. So I'm just going to put a placeholder, say insert SRL here to output register 6 to hex displays. Okay. So I'm going to save this. Let's see, can I put it on, I would say, no. Yeah, I want to put it in save as, put it in lecture stuff. There we go. Call it convert.s. Then I'll assemble it. Okay, and let's check it out. Let's see if it works. So notice the first thing that happens is that load immediate got treated as a pseudo instruction because that 429 million was too big to fit in the 16-bit immediate field. So it had to take this instruction and split it into a load upper immediate to load in the upper bits, and then an OR-I instruction to load in the lower bits. Make sense? So this is the reason why we're doing LUI. You guys might have, I don't know if you looked at, you might have wondered why we're doing LUI. That's kind of an obscure instruction. Well, it's because of this kind of thing where you have to be able to load a big number into a register. Okay, and then, so then we have an add IU, right? Also kind of obscure, but U is so it doesn't trap on overflow. And I is because we need to get the immediate. So there's your 10. So the 10 was only one instruction. The load immediate got translated to just one instruction. Then we had this big number, again, got converted to a pseudo instruction. And I think all the other ones are machine instructions, right? I don't think we have any other ones in here. Yeah. Okay, so let's start walking through it. So, oh, I didn't mean to do that. Restart. Okay, one at a time. So there's register 1 gets, oh, by the way, this is why you don't want to use register 1. Notice that it just, if I was using register 1, it would have just clobbered it here with the pseudo instruction expansion. Okay, so there's register 2. That's the number, by the way, in hex. The 0.1 is 19999999999A in hex. All right, so let's see, another load immediate. Okay, then I'm going to multiply, move from high 4, move from low 5. So 4 should have the whole part of the product, which should be the number I put in with the rightmost digit taken off, right? Is that right? Is that what it is? 4? Oh, I gotta, hold on, I gotta convert. I gotta say, values displayed in hexadecimal, turn that off. Okay, so if you look at register 4, check it out. 2, 3, 4, 5, 6, 7, 8. Remember there was a 9 there originally? The 9 got knocked off. And I'm going to try to recover that 9 with the second multiply and a move from high 5. Did that work? Oh, I got negative 1 in there. Fractional part was 5. Oh, I screwed up somewhere. Okay, so let's go back. So after I multiplied 4 by 2, then, oh, by the way, if you look in Mars at the bottom, you got high and low down here. Oh, I think I know what happened. I always make this mistake. When you do this, you have to make sure that you use multiply unsigned. Right, and you might say, well, why is that? It's because when I did that multiply, 4 and 2, actually I think it was the second, it was the second multiply that screwed me up. Because after I did the first multiply, the fractional part, if the fractional part was more than 0.5, now think about this for a second. If the fractional part was more than 0.5, what does that mean? It means that the leading bit was 1, right? Because remember, the first fractional bit carries a significance of 0.5. So if the fractional part of the product was greater than or equal to 0.5, which in this case it was, right? What was the fractional bit? It was 0.9, right? That 9 was the number I knocked off I want to recover. So I got 0.9, which means the most significant bit of the fractional part was 1, which looks like a sign bit to the multiply, right? So when I did the second multiply, it saw a negative value there, right? When it wasn't negative, it was a positive number. This is an unsigned. I'm doing this as an unsigned calculation. So
you want both of them unsigned then?
yes, yeah. So they should both be unsigned, and I always make that mistake. All right, so I'll make it mult u and mult u. Save it and reassemble and rerun this guy. All right, so now I'm going to step it down past that second multiply. And now register 5 should have, 9. It worked. See? So that 9, you see, in fact, you could see right there. There's the 2, 3, 4, 5, 6, 7, 8 above it, and right below it is the 9. So I got them in 2 different registers now, right? So then I'm going to take that 9, and I'm going to shift it to the left. So register 5 now looks like a negative value here because it's showing it as signed. So if I switch it back to hex, check it out. There's the 9. It's up on the left-hand side, right? And when I do this again, which I don't have the code to do it yet, I haven't pasted the code yet, but as I do this, that 9 is going to work its way down until eventually it stops. It stops on the right. And can I test that? Yeah, I can just copy and paste that real quick here. Just take me a minute. I want to do this 8 times because we don't have. This is because we don't have 3, 4, 5, 6, 7, 8. We don't have branch instructions, so we're going to have to just unroll the loop. All right. I think I got that right. Assemble. And let's run it. And what we're looking for here is register 5. Oh, sorry, 6. 6 is the one that we're actually building up. Okay, there it is. There's the first digit. You see that? In register 6, I got the 9. And then, I shifted it down and I added the 8. See? I'm going to keep going. I'm going to add the 7 here pretty soon. Boom, 7. You see how it's building that result up? It's filling it in. Okay, well there's my program. So now I'm done with that. I'm going to export this. I'm going to say dump memory. I'm going to dump the text section. Text means code to not binary but hex format. Dump the file, and I'm going to call this program.hex.bin. I don't know, .dat. I don't know what to call it. Program. Let's call it .dat. It doesn't matter. And if I open up that program.dat with a text editor, open it with Notepad here. No. There it is. That's what it looks like. These are all the instructions, the encoded instructions. So now I want to build a Verilog file that will store this program. So I'll say cpu.sv module CPU end module. Okay, so first thing I got to do is I got to create a logic to hold my program. So remember, when you do a RAM in Verilog, what comes first? The width or the depth? Anyone remember?
It's opposite normal, right?
Yeah, the normal way to do it is in like C and Java is depth.
Depth first, so width first.
But this is, we're doing width first. Yeah, so width is going to be 32 bits, which is 31:0. And then I'll call it, I don't know, instruction memory? Or, yeah, it's fine. Memory, and then my depth comes next, and that's going to be 4095 to 0. I have 4,096 instructions in there, right? And then I can say initial, begin. I'll just say initial. Yeah, begin. Initial, begin, and end. And then I'll do read, mem, h, instruction, memory, and I think the first parameter is the file name, right? Program.dat, I think I called it, right?
Yes.
And I think that's it. Yeah, cool. Okay, I'm going to go ahead and see if I can compile that. So I'll vlog it. It worked. Now I'll vsim it. No vopt. CPU. I just want to make sure this worked. Which in ModelSim you can look at RAM. Oh, popped up already. In ModelSim you can look at RAMs. Okay, so if you click, well, you see I'm clicked on CPU over here, and I've got instruction memory over here. It's the only thing I declared. So I'm just going to say add that to the wave, and then I'll run it. Just one tick. Then I'll go to the waveform viewer. Oh, I shouldn't have made it that big. No, it's all right. So scroll down to the bottom, and I've got nothing in there. Okay, it didn't work. What happened? No such file or directory. Cannot find program.dat. Cannot open readmem file program.dat in read mode. Did I not call it that? Program.dat. What directory am I in? Let's do a pwd. I'm in the wrong directory. That's why it didn't work. So I'm going to cd to lecture_stuff, not staff, stuff. Cannot change directory while simulation is in progress, so I'll have to stop simulation. End simulation. Are you sure you want to exit? Yes. Okay. Now I can cd to lecture_stuff, and then I can restart the simulation. I just have to, I might have to recompile it actually, because I think I must have compiled it in the wrong directory too. So vlog cpu.sv, and I got one error, one warning. What's the warning? Failed to open CPU. Where am I at here? Oh, okay, hold on. Let's copy /cpu.sv to here. Okay, now let's try that. Yeah. There we go. Now I got it compiled. Yeah, so this is a common thing that happens to everyone, by the way. Well, maybe not to you guys, because you'll be using Charles's script. But because I did this manually, I started ModelSim in the wrong directory, so that's why I got screwed up. But now I'm in the right directory, so I got the Verilog file and the DAT file in the same place. So now I just have to just to go over here to work and right-click that and say simulate without optimization. And then I can drag in my program RAM, which right here I say add wave, and I've got that there, and I run it for a tick, and then I hit the plus sign, scroll down. Yep, and there's my program. It's all there. Well, it looks like it's all there. It's hard to. It looks like I've got 69 instructions. Okay, so now I've got that loaded. If I go back to my Verilog, cpu.sv. Okay, so now let's put a program counter in. So logic, how big's the program counter got to be? Well, it's 4096, so that's 2 to the 12th power, right? So I got to have a 12-bit program counter for that. So I'll say logic 11 down to 0, PC_fetch. I'm calling it PC_fetch because it's in the fetch stage. And then I'm going to have it access the program. So I'm going to have always, it's going to be synchronous. So always _ff at pause edge clock begin end, and I'll say instruction_ex gets instruction memory at PC fetch, and hey, while I'm at it, I'll just reuse the same always statement and say PC_fetch equals PC_fetch plus 12 apostrophe B1. So that'll take care of incrementing my program counter. I also have to declare the instruction EX, so logic 31 down to 0, instruction_EX, and I need a clock too. So I don't have a test bench yet, so I'm just going to do the clock in ModelSim. Any questions about this? All right, so save that. Go back to model sim. I'll re-vlog it. Vlog cpu.sv. Undefined variable clock. Oh, that makes sense. Okay, logic clock. All right, vlog. Good. Let's restart. Now notice over here, I don't have that clock and I don't have the instruction yet listed here. So, but if I restart the simulation, they should pop up here. Yep, there they are. So I'll bring up, I'll just go ahead and say add wave for these guys. And then the clock, I'm going to right click that and I'm going to go down here to, oh no, I cannot see. Oh, let's rescale the display. Will that work? Can I scale it to 100%? Is the projector going to puke? Looks okay. All right, back to model sim. Model sim. Okay, now I can right click on clock and should be able to see. Oh, now I've screwed up the X server. Okay, well that's not going to work. Okay, well then I'll have to do this little hacky. Normally you just right click on there and you can say, you could tell model sim to make it a clock.
You can do it from the waveform screen also.
Okay, let me try that. Oh yeah, there we go. Perfect, thank you. Yeah, nice. There it is. All right, problem solved. Now I can run this guy. Okay, so as you can see, its clock is going, but the PC never got initialized to 0. So if the PC started out as undefined and you increment it, it's still going to be undefined. So we need to initialize the PC. So I can do that easily. I'm going to need a reset signal now too. So I should have made these inputs instead of making them logics, but I can move them to the input list easy enough. Okay, so I'm going to add pause edge reset to my sensitivity list, and I'll say if reset, then begin, and I'll say PC fetch equals 12'B0, and for that matter, I'll say instruction underscore, I'll zero out the instruction while I'm at it. 32'B0, end, else, begin, do that, end. All right, save it. Back to model sim. Model sim. All right, do another vlog on this guy. Okay, that worked. I'm going to set up the clock with the up arrow, and I'll force reset to be, force reset to be 1. Oh, I didn't restart yet. I got to restart so it sees reset. Okay, force reset 1. There it is. Force the clock, run, force reset to 0, and run. All right, okay, so we zoom in. Where's my zoom? Okay, so now I've got an instruction stream. I got program counter here, incrementing, 0, 1, 2, and I've got instruction EX, which, hold on, make the name shorter. Here we go. Instruction EX, there's the first 2 instructions. Now notice that I have 3 program counter values, but only 2 instructions. That's because of that delay. But if I keep running this, run it a bunch more times, there we go. There's my stream of instructions coming out of there. So I've got, so this first instruction that's here is the 0th. Right, it's the first instruction, instruction 0, but the program counter is already 1. So the program counter is 1 when the instruction coming out is 0. Why is that? Well, remember that I've got this is PC fetch, and this is instruction EX, right? So this PC is a fetch stage, and that's the execute stage, which is why that's what indicates that whatever's on instruction is one cycle delayed from what's on PC. Yes?
So basically with this, we're able to kind of backtrack and say like, okay, like maybe like at PC fetch like 20 or something like that, we can go back to our message and be like, okay, the 20 or the 19th instruction is the one that we're having an issue with.
Right.
Line like 19, for example, and that's the one that we want to fix.
Yep.
So that's
Yeah, that's exactly right. If it's a problem in instruction 20, then you have to go to 21 when the program counter is 21. Or if the instruction is 19, then you have to go to program counters 20. And that's where you want to click your mouse.
Yeah, so these do translate one-on-one. It's not like these instructions being broken down into more steps and then send to mouse or anything.
No, it's literally just that simple. If you just look for the program counter and then just basically add 1 to it, and then that will be when that instruction is being executed. And that's usually when the bug is happening, in that. Now things get a little bit more complicated once we add the branches, because the branches are delayed by 1 cycle. But I'm going to talk about that in the next. That'll be the next part. Okay. Any questions about this? So we verified that we've loaded our instructions, our program. So we wrote the program in Mars. We exported it to a hex. We loaded that into our instruction memory. We added the program counter. And now we have essentially the whole fetch stage is done. Now we just need to hook this up to an ALU and a register file. So how do we do that? Well, I'll create my register file right here. I'll just say reg file 32 by 32, my reg file, and I've got a bunch of stuff. Now this part, let me see, v split reg file. So I'm going to go over to the reg file. So here's my reg file. I'm going to copy that, and I'm going to just paste it here. And then, let's see. Yeah, I'm going to, I don't know, this is kind of ugly, but I'm going to say, I'm going to just add dots here so I know what my ports are and I don't forget any of them. So dot, 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 write data as a dot, and then I've got read data 1 dot, read data 2 dot, and I'm going to put some, let's try to line these up a little better. Okay, now when I hit equals equals, it's supposed to auto indent, and watch, it's going to, oh, it worked, cool. All right. There we go. Boom, boom, and okay. And then I can add parentheses to each of these, and then I just after that I just plug in the actual connections. All right. So clock is clock. Okay. Read address 1. Now remember. It doesn't matter if I'm doing an I-type instruction or an R-type. The read address 1 and 2 are always the same. It's going to be instruction _EX, and then what's the first read address? It's the RS field, right? Which is what? Bits 25 down to 25? Yeah, 25 down to 21, right? Yeah. Why doesn't it? Oh, 26. Wait, why am I drawing a blank here? It's 31 down to 26 is the opcode, then 25 down to, yeah, that's right, 25 down to 21. That's the RS field, right? And then read address 2 is the RT field, which is instruction _EX 20 down to 16. Cool, all right. And then read data 1, that goes into the ALU A port, right? So I'll have a signal here called A _EX and B _EX. That way, when I put the ALU in, well, I'll just do that now. ALU, my ALU, and A is AEX. B is going to be BEX. op will be op ex, and because these are all execute signals. ALU is asynchronous. ALU is combinational, so it's I'll just everything connected will be ex. Then we have low, so I'll have low ex, and might want to rename these later, but I'll put placeholders, and then high ex. Is that it? Oh, and 0, right? Yeah. 0 E. Oh yeah, shamped. Good call. Yeah, shamped. Dot shamped is going to be shamped ex. There we go. Okay, so I've got A, B, shamped, op, low, high, 0, and that's it for the ALU. Okay, so I've got that, and now I need to declare my A and B.
Read address 1, you have a bracket closed with parentheses.
Oh, yes, thank you. Yep, good call. It saves me an error message. Come on, buddy. Insert. There we go. All right. Okay. So I have to declare all those signals. Logic, 31 down to 0, A, EX. And I'm not, you don't have to name your signals this way, by the way. This is just, in fact, I might end up renaming these. 4 down to 0 is shamped EX. And then I've got 0 EX and high. I'll just actually add the high and low to the end of this list. High EX and low EX. All right. Okay, cool. Okay, and then I'll need the write enable, the write address, and the write data are going to be write back. Those will be write back signals, right? So I could also add those. Let's see, reg write underscore write back. So I'll have a signal for that, reg write underscore write back, but I'll also need a reg write underscore ex as well, because that signal reg write is going to be generated by the control unit in the execute stage, right? But then it's going to get delayed and it'll become the write back underscore write, the reg write underscore write back in the next cycle, right? So this signal is generated in the execute. This one's going to be the delayed form of it, which I can do right here. I can just say always. In fact, maybe I'll just put everything in that one always statement.
Are those logics all supposed to be only 1 bit?
Yes, 0, reg write ex, those are 1 bit. That's right. These ones are all 32 bits because I have them all. Logic 31 down to 0. All of these will inherit the 32 bits.
Yeah.
So I can add another always statement for this, or I can just start adding to this one. I don't see any reason why not. I mean, it should be commented better, obviously, but I could just stick reg write underscore write back equals reg write underscore ex right there, and I can also reset reg write here as well. While I'm at it, reg write back will be 1'B0. So that way I can reset reg write here, and I can set it down here. So that way I keep everything in the, I have this kind of like one giant always statement I can use for all my registers. Or like I said, you could split it into multiple. It's up to you. It's whatever your style is, whatever's easiest for you. Okay, so I've got reg write hooked up there, and then these guys will also have underscore write backs on them after them. Okay, so what do I need to start running this? What is the minimal set of stuff I need? Actually, I'm probably pretty close, except my program has my program's got R-type and I-type instructions, and right now I just have this set up for R-type. And you might say, well, how do you know that? It's because of this. The ALU, the B input on the ALU is only hooked up to BEX, which is what's coming out of the register file, right? So in order to get I-types working, I need a mux between these two guys. So a better approach would be to write a test program that only executes R instructions, right? Which we give you, and I give you a sample of that in the slides somewhere. Right here. So here's a test program you can use that will only exercise the R-type instructions. So you can, you don't have to worry about the I-types. You guys follow that? So what I'm saying is the program I wrote to do the conversion won't work until I have both the R and the I-type logic put in. So if you want to start out with just the R-type version, then you can use this program instead. In fact, how hard would it be to finish that off? I just need to finish the write back stage. So for R-type instructions, the write address is going to be instruction underscore, well, I don't want to get it right from instruction. It's going to be write address underscore write back. And that signal will be set in this always at pause edge clock. I'll say write address underscore write back is going to get instruction underscore EX bits RD field, which is 15 down to 11, right? Yes. Right. So instruction EX 15 down to 11 is going to go into write address write back. This will just be a 5-bit signal. Right? So what I'm doing here is I'm selectively delaying parts of the instruction. In other words, in the write back stage, I'm going to throw away everything in the instruction except for this field, right? So all the other bits will get thrown away, will be gone when the instruction moves into write back, but I'm going to retain those 5 bits for the write back. And what's write data going to be? That's going to be low underscore write back. So likewise, low underscore write back is going to be just low underscore EX right there. So that'll be delayed. Now you might say, hey, do you want to reset those to 0 on a reset? No, I don't care. Well, why did I reset reg write? Well, reg write is a destructive signal, right? You don't want that coming up as a random 1 because that could, well, I don't know, it's kind of dangerous because it writes the register file. But if reg write is 0, then write address is a don't care, right? So as a result, I really don't care about resetting write address because as long as I predict reg write, then that write address is going to be a don't care. Likewise, low write back as well. Okay, I think that's just about everything. 0 EX I'm not using, or high EX yet, because I'm not. I haven't implemented the move from high, move from low yet. Although those are part of the R-type instructions, so those will eventually. I'll have to put that in. Yes.
So for the lab, would you recommend trying to just get everything running with R-type first and then move to that?
Yeah. Well, it's a little confusing because in the past we had one lab was the R-types and then we had another lab was the I-types, but in this semester we're putting them together. So, but I think it's a good idea it's up to you guys how you want to do it, but I think the easiest way to do it would be to do the R-types first and then do the I-types.
You don't think it would be complete us getting tripped up, like doing one and trying to go back and fix things rather than just doing all of
You could just, I'm not sure what the best way to do it is. I think doing it R-type, getting the R-types working first is better, because then you kind of build like a skeleton, and then the I-types is just essentially adding muxes to what you've already got. Having a working R-type is pretty easy. In fact, I've basically done it. The only thing I have to add now is the control unit, and then I've got it done. The control unit, though, it takes some time, though, because you have to have an if condition for each instruction. And how many instructions are there? There's 32 total. How many R-type instructions are there? So I would need a line for 1, 2, 3, 4, 5, 6, then 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, and then plus the move from high, move from low are going to be added to that as well. So 17, there's 17 instructions. So I can start adding those in my, I could say always underscore comb, and I can just stick my control unit right here and just say if instruction. Now, if I'm only doing R types, I don't have to check the opcode, because remember the opcode is always 0 for R types. All I have to check is the function code. So I'll just say, what's the function code? 5 down to 0. So if that is 6'B, and then I need to pull the reference card here. I think this stuff is here, right? Yeah. So if you look for like add, oh, actually it's right here. Yeah, add. The function code is 20 in hex. I don't know, you probably can't see that, but. Yeah, it's on. I need to add it as a download. If you go to, you can also on Dropbox. There's a separate. Actually, it's probably better that you use the other one. They both work. But if you go to Dropbox, we have another site, a little reference card here somewhere. Yeah, MIPS CPU spec available here. You click there, and the function code is. So that 20 is right there. So there's a 2 and 0. You might say, wait, 20, it should be 8 bits, because there's 2 hex digits. But no, it's actually 6 digits. So the first one is just the 2 bits. The most significant is whatever's the remainder, right? It's 2 bits. So you could just follow. This is a better one to follow. So I already forgot. All right, 1, 0, 0, 0, 0, 0. So that's my add. And I'll just do that one for now. So op underscore ex is going to be the 0100 that tells the AOU to add, right? Do I have op ex in here? Yes, I do. I didn't declare it yet, though. Did I declare it? How about I didn't declare it? No. Okay, so I've got to declare it. Logic 3 down to 0, op underscore ex. All right, so I got the add operation. And what else? Oh, reg write underscore ex is going to be 1, because that does write a register. Oh, shamped will be a don't care. Shamped underscore ex is a 5'B XXXXX. Anything else? I think that's it, right? Op, shamped, that takes care of the ALU. Everything else is pretty straightforward, right? Yeah. Okay. I think I forgot to declare something else too. I might be missing a declaration, but of course I'll get an error when I compile it. But that's it. I mean, that's basically that's the CPU. That's a whole CPU that can do add instructions. And then adding additional instructions is just a matter of adding to your control unit down here. So this is all in one, one file. I mean, this probably makes Charles sick, but it's a single file. Well, you used to have an appreciation for single file C libraries. This is a single file CPU.
I mean, as long as you have comments.
Yeah, I didn't comment this. It needs, but we could comment it. I mean, we can comment it. You can put comments above, each one of these lines of code.
I mean, at least you lined up all the parameters, right? So
Yep.
that counts for something.
Yep. Yeah, I probably should have tabbed out these names here too.
Will be available in your online lecture as well, right?
Yes, yeah, I'll post this. I can post this on Dropbox too, although I can't guarantee it's going to work because I just did it off the cuff, but it gives you an idea where to start. Yeah. So yeah, this I'm pretty proud of this in like 35 minutes. Design a CPU that only does one instruction, but also, by the way, some of these things are going to have to be moved up to the inputs and output list, right? Like clock and reset, I have them declared almost as if this was a test bench, like they're local signals, but these should be up here on the, you guys with me on that? These will be inputs and outputs. Input, clock, input, reset, right? Those should be up here, and then I can take them out of here. Yeah. And actually, that's about it, except the GPIO for the switches will have to come in as well. And I indicate that, by the way, on the design. I have GPIO as I show where that comes in and where it goes. I'm just about out of time here. Any other questions about this CPU? Hopefully this gets if you haven't already gotten rolling on this, I'm hoping this will help you get started. Any questions about Mars too, that stuff, or about the algorithm to do the base 10 conversion? So what your design should do when you're done with it is you should be able to put on the board, and you should be able to flip the switches, and it should come up as you should see a decimal number come up. So again, like I said, if you put up 4 switches, it should say 1.5 instead of F, right? 15 instead of F. And if you put them all up, it should say 262,000 something, whatever 2 to the 18th power minus 1 is. About 262,000, which is 6 digits, by the way. You can't get a bigger than a 6-digit number, unfortunately, even though my Mars code accommodates 8 digits, right? Yeah. Oh, and also, if there's like leading zeros, the Mars code should accommodate that, because when you do the multiplies, you'll get a 0 and high, so it'll bring in zeros. Okay, well, great. Then we'll see you in lab then.